from the portal.
Okay. Welcome all to the special session on mathematical methods and techniques in signal processing. So this is the first time we are having a special session which is going live in air. There were a bit of technical difficulties here with the team here on ground. So, we are slightly delayed, but I think we can get started now. So please let me know if everyone is able to listen to my um, listen to my talk here, and then if you have, you can post questions which will be collected live by the TAs, and then we can begin with this. So I think I would like to introduce the TAs here. I'll just briefly say something here, and you can see their faces, who they are. So this is Chaitanya Kumar, who's a TA here. Can you see him? I think this is something which.
Just 10 seconds.
Okay. So this is Chaitanya Kumar. You can sit down. You can show your face. So he's one of the TAs who is handling this course, and he's a senior PhD student. Then we have Priya Nadkarni. So Priya is another TA who is handling this course. And then she's also a PhD student here with IASC. Then we have Amrita Machi Reddy. So she's also a PhD student who is handling the this course as a TA. So welcome all the students. Shaunak, is he here? It's not. Yeah. So there's Shaunak Roy, who's not in here, but I think we can go. We can get started. So the purpose of the special session is basically to have a little more of interactive feedback with students. I mean, you have done at least 8 rounds of assignments, and the 9th assignment is already given. And you might be wondering who's behind the scenes. So I think we are all, as a part of the team. I'm Shain Srinivas Agarani. I'm a faculty. I'm handling this. And together with myself and my team of 4 TAs, we are conducting this MOOC course. So feel free completely to ask questions. Welcome all of you to this special session, and make use of this special session to ask questions, whatever you have, get those clarified. And if it requires any detailed calculations, etc., I can always take it back, and we can answer your questions by email. But if you have any general questions, discussions, difficulties, whatever you face, you can basically ask the questions, and we'll be happy to take questions. Can everyone see this link? Are you all able to see the link? So if you say yes, I think we can figure out if you're comfortable. Amrita, do we have any questions? So how many students are online? Okay, it's fine. It can be very informal. It's okay.
Right now there are two people.
Rohit and then Vijay. What about Afzal?
Afzal, Afzal also showed up. I'm not sure if he has seen this.
Okay.
So what is a chirp Z transform and what are its applications?
Okay. What is a chirp Z transform? Chirp transform and what are its applications? So I think it is basically the chirp transform is has its applications in speech processing and also mainly in speech processing, because the ear drum, you can think about it's a logarithmic basically spacing of the frequencies, right? So if you this is basically um, akin to if you think about the tympanum, the eardrum, and you open up the eardrum, and if you can observe the frequencies, it is basically a logarithmic spacing of the frequencies, and the chirp Z exactly does that. So basically, it is logarithm. It's a transformation which places a logarithmic emphasis over these frequencies, and that is basically attuned to the hearing in the acoustic. From the acoustic signal processing perspective, this transformation can be used to basically resonate to what is done similar to the human ear. So, hope that answers your question. And the details of how the mathematical specifications for transformation, you can refer to Oppenheim Schaefer's book, and there is a link to the exact definition of the transformation. But this is essentially what the chip transformation does. Linearly modulated or exponentially in the log domain, it is linearly modulated. So this question was from Sita Singh, right? Okay. Okay, great. So which part of where are you from, Sita? Which part of India or the world? We don't know here. So we can introduce yourself, which part of the world you're from, or which part of India you're from, which college or university, so that it gives us, it makes us much more interactive. It is just like a radio. Imagine like we are just getting your comments here on the web from through the web, and I'm just answering your questions. I would like to know your background as well. So feel free. Okay, now it's 31 viewers. Okay, great.
So
Bhopal, Madhya Pradesh. Okay. And the TS, you can also feel free to interrupt in the middle, and we can make it a really informal set of discussions. So feel completely at free. Okay. Questions, please. So make use of this time. We will have more of these. but I want you to make use of this special session. We'll ask questions from the course, and if you have any questions to the TAs, you're most welcome to ask. Feel completely free.
Is working.
Working professional. Okay.
There's a question by Shivakumar.
Okay. Say that. Can you?
What is the best?
So there's a question from Shivakumar.
Mm-hmm.
It says he asks what is the best suitable signal processing techniques for fault diagnosis of rotating machinery?
Fault diagnosis of rotating machinery. So a good question. Fault tolerance, and I mean, normally defects, if you think about it, they appear as artifacts in some way. And the rotatory machinery, I mean, even if it is rotating, you can also always unfurl it in the form of a linear signal, right? I mean, though it is rotating target, the signature it brings in as it goes through a linear. You can have a linear component there, right? I mean, if you fix a point, let this be a rotating point, and let a rotating machine, as it goes through the circumference, it will translate itself linearly over time. So I suggest that you could use wavelets basically to figure out any artifacts, etc., in the linear as it sees a linear spread. Another way is to modify via possibly circular wavelets. This is an idea that I have that I can think about. So I hope this answers your questions, because any fault is basically an aberration or a high frequency component, and I think wavelet can hopefully do that. Or you can even take as the initial step, you can just do a fast Fourier transform, just observe the high frequency side of this 50, and then you may see something. And with the rotatory parts, mainly what you will see is you will see this periodic motion. There is a periodicity in the signal, right? And the periodicity will reflect into the spectrum, which is, you have to look at the baseband spectrum and from there arrive at what is the right way, right? There are also radon transforms and some of these other things which make use of radial symmetry. So I would try the FFT first, figure out if I can do something. Then I will do the wavelet, and then if there's radial symmetry in the parts, etc., you might even think about radon transform, and post that you may do a wavelet decomposition to figure out if there is anything. So you may have a mixture of two transformations.
So adding to what Professor said, in fact, I did some study on this fault detection of some of the machinery.
Okay.
So the way they do it is, as Professor mentioned, we look at the periodic signals and look at the responses at the harmonic frequencies.
Okay.
So and see if there is any deviation in the response in those harmonic frequencies from the desired or non-faulty system, and that is one way. So it seems like Fourier transform
should work.
Yeah.
But I suggest you to experiment.
Yeah.
Suggest you to experiment. If you think the FFT doesn't work, then go through sophisticated transformations as and when required. But the geometry of your device, everything really accounts for what it has to be done, what needs to be done.
So there's a question from Abzal.
Okay.
He says, I'd like to know about sampling.
Any specific, I would like to know about sampling. You've asked me a very broad question, Afzal.
Not just a brief.
Just a brief clarification. Okay. So here is the goal of sampling. I mean, I'll give you a historic perspective, and for those of you who are who have logged in live, right? I think it's a history session. So the idea of sampling is very important, because when you think about an analog signal, it has a lot of information, right? Analog signal, you really require infinite precision to store the analog signal and process, etc., etc. In practice, we need to get to discrete time, because we deal with finite precision, right? Even if you think about your computer and a sophisticated computer, you are a 64-bit machine, which is still fixed point, right? You're really not floating point. You have a very high resolution, which means you can access a 2 power minus 64. Now, an analog signal is basically made discrete time via the act of sampling. So basically, if I have an analog signal like this, right, I have to sample at greater than twice the maximum frequency contained in the signal, and this is basically the sampling rate, and this is precisely greater than, because if it is equal, then if you're sampling at 0 points, for example, if you have a sine wave like this, right, if you sample at exactly this phase, then you'll sample here, you may sample here, you may sample here, you may sample at the 0 crossings. This is not there. So if it is equality, then there is a trouble, as you can see through this picture here. So therefore, we strictly restrict it to be greater than 2 times the maximum frequency. Basically, you have a pulse that you sample. You have a signal here, continuous time signal. You sample at certain rate fs, which is more than twice the maximum frequency contained in the signal. And this is how one can think about it. I mean, this small, this pulse is very, very narrow, and you can say as the time is really very, very small, and you can treat this almost as an impulse, right? I'm just going to put your samples here. So on and so forth, right? So these are your samples that you're at these points, right? You're capturing this, capturing this, capturing this, capturing this, so on and so forth to the rest of the signal, right? And now these samples can be quantized, right? Can be quantized, and you can store it, or you can process it, and you can do whatever you want. So basically, you have taken a continuous time signal, and then you are sampling, and then you get, it's like a switch. I think I'll have to put this as a switch as well. And then you get discrete time samples. This is the idea of sampling. And then from these discrete time samples, I should be able to reconstruct continuous time as well back. And that you can do so using ideal low pass filters, which are Nyquist filters. So this is the whole idea of sampling. So as you can see now, when you have these discrete samples, you can process it on your computer. You can do whatever you want on a computing device. And then you can filter it out. You can filter the noise. Many sophisticated techniques can be handled using discrete time signal processing. So that's the whole idea why you need to sample. And this was a question people raised in the 1940s during World War, because they wanted to do this is how the field actually evolved. I hope this gives you a clarification about what sampling is about.
So next there is
is he okay with it? Does he have any more questions? Afzal, are you okay?
So the next question is by Eileen Sengupta. Hope I pronounced it correctly.
Eileen
Sengupta.
Okay.
So in digital speech processing, what are the best signal processing methods to separate signal from noise? Is there any method that identifies the different phonetics?
Okay, in digital speech processing, what are the best signals? Most of the digital speech processing techniques have been through statistical methods. And to separate signal from noise, you basically have to figure out, basically noise is, again, what kind of noise, right? Is it high frequency noise, or is it low frequency noise? So you can do a Kepstrom, right? You can take the log of the transformation of the transformation. You do a Kepstrom transformation. Basically, you have a signal plus noise. You take the logarithm of this thing, right? And then you can you can filter them out, or you can even treat adaptive. You can use adaptive signal processing techniques. Basically, you remove the correlations present in the noise, and then that will land up with a white noise. And a white noise you cannot do better than that. You have to live with white noise. So the whole idea about most of these signal processing techniques is to basically reduce any correlated noise to a white noise, and that you can do using whitening filters, etc. And post this whitening process, you have to live with that noise. And you can suppress if you know certain harmonics are bad, because speech is basically low frequency signal. So if you know there's the certain properties of noise, whether it is high frequency or etc., you can null it, you can notch off certain portions. If not, you have, if it is white noise, you have to live with it. There's nothing much you can do. And usually people do this with speech enhancement techniques, right? When you have to enhance the speech, you treat signal plus noise, and you basically do a subtraction on the correlated noise. You decorrelate the noise, do a spectral subtraction of that noise if you know these certain properties of the spectrum, and then what you have is your residual signal. Kepstrom techniques, I would advise you to look into closely into Kepstrom techniques or homomorphic deconvolution, some of these ideas.
Okay. So I have an extra question on this. So we actually model the speech signal as a linear feedback model, right?
No, it's basically random noise through a linear, feedback in ARMA model. Yeah.
So linear feedback model. So that is how we model. So now, if we so we have studied in our earlier courses on this signal modeling. So if we are able to model that as some linear feedback model, does that somehow handle the noise also present in the speech?
Noise is going to be get modulated. That's the whole idea. Because if you think about a signal flow graph, so every portion of, imagine a cascade of filters in the signal flow graph, and each cascaded filter is basically like it vibrates to a phonetic this thing. There is a certain frequency, the Forman frequency, etc. Right? So this reverberates to those frequencies. So it's white noise being sent through a sequence of resonators. And to sequence of resonators, you can construct the speech signal as such. And that's the whole idea. So if you're thinking about cancellation of noise, that means I know the properties of speech in a certain way and I want to cancel, you can think about these models as well, wherein you can say that another signal is coming from this particular way and I want to cancel it. If you know exactly what the signal is, exact speech utterances, that is one way. So suppose I know hello, and I know hello plus noise. If I can model hello using acoustic filters, so that is S hat of n, that is my desired signal. So I can use an adaptive filter to basically cancel out. I know what my desired signal is. I know what my input is with noise. So I can come up with an adaptive filter which can basically, so I'm using another form of modeling, signal modeling, and then being able to cancel it out from there. So I hope this answers your question. Okay.
So Rohit asks about decimation. How decimation is not invertible?
How decimation is not invertible? Rohit, I mean, you've downsample, right? We discussed that you can reconstruct the signal from decimation, provided it satisfies pi by m. If you're an M4 decimator, as long as you're able to reconstruct from the decimated samples, it's fine, as long as your sampling rate is as much as that. But in general, it is not. Because you simply take a signal and you downsample, you cannot invert it because you've lost the interim samples. To reconstruct it, you'll have to have an interpolation filter that is possible provided you are within the sampling constraints, sampling rate constraints. Otherwise, you cannot. So Afzal said no, just a brief clarification
on the sampling earlier question.
So okay.
So the next question is again by Rohit. He asks why we can't say periodic impulse train as power signal.
I don't get that question. What do you mean by it's a power signal?
Yeah, I think we'll revisit. We'll ask the clarification. So meanwhile, Satyaprakash has asked, can orthogonal EMD and ensemble EMD techniques be implemented simultaneously?
What is EMD? Can you explain this out for us?
Yeah.
It's empirical mode decomposition.
Empirical mode decomposition. I am not sure I am comfortable. I have seen these techniques. EMD, I think there's something technical here. Unless you specify mathematically what it is, maybe I can think through it. Orthogonal EMD ensemble, where do you see this? Afzal too, I don't know whether he got a clarification. Just empirical mode decomposition. I don't know what you mean by that. So
Second question is, it's an adaptive technique based on Hilbert transform.
okay, it could be. I have no idea. Maybe we'll take this question and we'll get back to you offline. Adaptive technique based on Hilbert. Adaptive technique, where is this Hilbert transform residing? What is the configuration of the system like? I think I'll need more details because I'm not active in this area. So Hilbert transformation is fine, but you know what do you do with that? Rohit says all periodic signals are power signals, except periodic impulse train.
So power signals in the sense, if you take average over a window, it is like if you take the energy, it is infinite in energy, but over a window.
Oh, if you take it over periodic signals are, yeah, I think probably basically you're averaging it over a window and then you let that, and therefore it's a periodic impulse train, right?
So his question is why we can't say periodic impulse train as a power signal.
So periodic impulse train, the impulse train is periodic. Periodic, what do you mean periodic impulse train? I mean, is basically you have sequence of impulses, and you say these sequence of impulses over a window is periodic. Is it what you mean? Why impulse train is not periodic?
Not power signal.
No, impulse train is just a train of impulses, right? I mean, that need not be periodic. A train of impulses need not be periodic, right? Unless you bring in a discrete time signal like this, and then I can have a periodicity here, right? Trivially, the period is 2. Is this what you're saying? I mean, this is an impulse train, and it is periodic with period 2. And of course, if you look at the energy of the signal is basically infinite, right? Because you add, if it's going on till infinity, this is basically, let us say this amplitude is 1, this is half, this is 1 plus 1 plus 1, infinite times is infinity, plus half, I mean, this is square. Let us say half square plus half square, so on. This is also heads to infinity, right? So therefore, you can't say anything about it. So therefore, this is an energy. The energy is infinity. So therefore, if you just look at a window of 2 samples, window about its period, then you can say it's a power signal because it is 1 square plus 1/2 square, which is finite. I hope this explains your question.
So maybe his question is also on continuous time signals, saying if you look at periodic impulse, whether it is a power signal or an energy signal. But I think it should be a power signal.
And say that again, continuous time signal.
So a continuous time signal, let's say if we have a sine wave,
right?
So it has a finite energy, equal energy in each period.
Right, but the energy it has is infinity. If you integrate it over time.
Over time it is infinity.
But if you,
over a period it is going to
if you did this 1 over t energy of the signal on this interval t, I think this is basically a power signal. And if you want to be careful, you might just let this limit t go into infinity. You could do that, right? So this gives you power. I should put the other equation other way around. Power equals this, right? So this basically will give you a finite power, but the energy is infinity because the energy it has is infinity. So
what I think is, as Rohit mentions here, amplitude is infinite for impulse. So essentially, I think he is talking about a continuous time signal.
I mean, amplitude is infinity, but you have to integrate when but the delta Dirac function satisfy a property that you integrate over that integral is going to be 1, right? You have to add that extra condition.
So it should be a power signal, continuous.
Yeah, I think that's right.
So I think it should be a power signal. Maybe if you cite sources where they talk that it is not power signal, maybe we'll look into it and clarify it a little later.
Yeah. Okay, great. Any other questions? So I have a simple question for all of you. How many of you are submitting your homeworks? Those that are viewers here, 23 of you, 23 viewers, are all of you submitting your homeworks regularly? It's very important that you solve all your assignments and be prepared for the exam. Yeah. One last. Okay, sure. Please go ahead. Please go ahead. Rohit has a question, I think, apparently. So.
Shivkumar.
Okay.
We have what happens if Rohit asks what happens if Hilbert transform is applied two
To
times
get back the signal back.
Yes.
So what happens if the Hilbert transform apply 2 times on the same signal, you get the original signal back. It's basically phase inverter. It basically shifts a phase shifter. Hilbert transform is basically a phase shifter. You two times phase shifting to get back the original signal back. So
so Shivkumar is asking about that vibrational analysis of rotating elements. So this we have discussed a little earlier.
We've talked about.
So Shivkumar, maybe you can view. We will post this video offline once this session is over. So Professor has mentioned. I mean, discussed these things earlier. Probably you didn't join the session by then, so you can watch it once a video is made available.
Okay.
So Sita again asks, where is analog signal processing used compared to digital signal processing?
Analog everywhere. Before you do signal detection, normally timing can be done in analog. Equalization in most communication systems. Once you have the analog signal, the first thing that you have to do is analog filtering. I mean, some sort of noise removal, out of band noise removal, etc. You may use continuous time filters, etc. So there you may do analog. All that is analog processing essentially. Any shaping of the spectrum, etc. Just before you have to sample, and from there you do equalization. You do timing recovery, equalization, etc. So just before that you do all analog signal processing. And mainly it is filtering these days. But if equalization is also wanting that it's comfortable that you can do it in analog, you can have analog equalizers as well. But often nowadays equalization is done digitally. So most I think to just filtering, I would say filtering is restricted to analog signal processing, shaping the spectrum, etc. And post that everything happens through discrete time signal processing.
So some of these, let's say if we have antennas where we receive the signal. So, for example, we use some kind of match filters, right?
Right. Yeah.
So those would be.
Yeah, those would be ideal for for analog
implementation.
Yes.
Graph signal processing.
Senthil Kumar Swaminathan. Give some applications of graph signal processing. I mean, it's a new area. I mean, I myself have not gone into, though I deal with a lot of graphs in other problems, particularly in coding theory, etc. I can think about, I mean, I don't know much to comment about at this stage, but I can think about the large scale networks, because basically, if you think about signal processing over nodes or edges, basically you can think about if you have a massive network, a graph is basically having set of vertices and edges and some flow information. So you can think about signals going through these edges in some way or the other, right? And if you think about signal processing, I mean, some kind of shaping or filtering or any of these things across the edges of the graph, one can think about applications one can think about graph signal processing techniques in a much broader scale. But I think it's a separate area to be discussed. But I think I can sort of give you a motivation with an example. Imagine you have a network of nodes. There are edges connecting all these nodes, and you have signals going through these edges. And any kind of signal processing, filtering, filtering of messages across these edges, or signal information to ascertain what kind of information that you want to relay via signal processing, control signal processing through these edges. I think you can think about applications of graphs in this context. So I hope I have given you a brief picture about this, but this is a separate area in its own, and it is, I think, a new hot area in signal processing. So, because people in signal processing have not looked into graphs. Mainly graphs have been used in coding theory, information theory, and these other areas, mainly for information transfer or basically from sources to a sink, information transfer from sources to a sink. And in the context of signal processing, one can think about application of these ideas. So I think this is my perspective about graph signal processing, but I'm sure there is a more mature information about this topic. So maybe we will cover it as mathematical methods and techniques in signal processing, part 3 of the course. So
Satyaprakash has a question extending Sita's question. So Satyaprakash asks, what is the advantage of keeping filtering analog? Advantage of analog filters.
So very good question. I think if you think about exponentiation, logarithmic transformations, etc., some of them can be possibly much easily done in the analog side than in the digital side, right? Because if I have to do a logarithmic transformation on a signal, maybe I use log amplifiers, etc., using op amps that naturally work in these exponential logarithmic regions to do the analog signal, to do the analog computation, right? So if you were to do it in digital, you have to think about Newton's method to approximate these functions, have them in a huge lookup table if you want the required precision, and then process it. So therefore, there are certain advantages directly to process it in analog, because computation naturally happens in analog. Another good example is, for example, if you think about optical signal processing, if you have two lenses which are kept 4f apart, you get the same signal back. That is, it's basically a Fourier transform. It does a Fourier transform, and you replicate at the same distance at 2f apart. You get another Fourier transform, so you can get back the original signal back. So a lot of these devices, whether it's optical, which is again analog, you can get a lot of transformations done, and naturally you can think about implementing log or exponential or some of these computations very naturally in analog, which otherwise would have to have lookup tables and some mathematical operations to do that. So I think that's the advantage of doing in analog. Okay. Hope it answers your question.
So Satya has one more question. While adaptive wavelet filters are digital filters. Okay.
While adaptive, what is this?
Probably as a part of this question on the analog. or Y adaptive.
Why is it Y or while? I don't understand.
So maybe it is Y adaptive filter.
Satya Prakash, is it Y adaptive wavelet filters or digital filters, or while? I don't see your question. While or why?
But wavelet filters, I mean, these should be convenient in implementing in digital domain, right?
Right.
Because they involve a lot of mathematical operations, which are more convenient to be implemented on a digital signal processor.
Yes, yes.
So these are
yes, as long as the order is tractable, that's all.
Yes. So yeah. While. So it is part of the first question.
So what is this?
Why do we use n-log filters? What is the advantage of keeping n-log filters while adaptive filters are digital filters?
Oh, yeah, I answered your question then.
So essentially, it depends on
the application in place, mainly for computation. Yeah.
And the other thing is wavelets is more mathematical in nature.
No, you could still have n-log filters which are mathematical in nature. Right?
Okay.
You could still have sophisticated your Laguerre filters, your Laguerre filter. I mean, you could have n-log continuous time filters for all of these. But I think the question of digital versus analog really depends upon if you want to store something and then process and do something else at your pace easily, then you may need those digital filters because it gives you a lot of flexibility. But sometimes analog computations like exponential logarithmic, even sometimes realizing some sophisticated operations are possible much easier with analog than with digital. So if that is a case and where your noise bandwidth is within tractable limits, you can go with analog filters than with digital filters. So I think that's how I would just feel the choice between analog and digital. Rashal Verma.
So Rashal Verma has a question. How initial condition affects the impulse response of mechanical systems? Example, aeroplanes or aircrafts, I think.
Ailerons of aircraft. What is this aileron? Is something new to us in aircrafts. How initial condition affects the impulses? Yeah, this is a good question. See, the initial condition really, if you think about system behavior, right, it is a natural response of the system. So that is given by the impulse response. So I give you an impulse to a system and I have an output. This is an impulse, right? This is an impulse. There is a natural response to the system, right? And if the impulse, if I give you any other initial conditions, then the system behavior can be different, right? It can, because there's a forcing function than the impulse. So depending upon initial conditions, you may not get the natural response of the system. You may get, it may be unstable depending upon your initial conditions, or it might be a stable, which might go to 0. That depends upon the initial conditions. Right, so this is a basic theory here. So, okay, air cart control system.
Aircraft control system. So ailerons are like
okay.
Some.
So ailerons, you have a.
So they are like control systems.
Basically, on the wings, you have a left force, you have a right force, you have a it's a good question. So basically, it's very important because the initial conditions have to be maintained. Because the output of the system can become, depending upon if the system, for example, is critically, so that depends on natural vibrations in the modes of the system, right? So if the system modes are linear, or stable, right, then you can expect that the impulse response of the system is basically is stable. It's BIVO stable. So if the poles of the system are, because they get perturbed, and if the modes are unstable, then any other input can give you a blown up output. So therefore, it really depends upon the output depends upon both the input transfer function and the filter, which is the system behavior, system modes. System modes can be stable, but the input itself, if the model for the input itself is unstable for whatever reason, that can cause basically bonkers on your aircraft. So
it is also possible that initial condition can trigger the modes of the system and cause the vibrations.
Yes, absolutely. because if you're resonating on something else, it can amplify completely. So okay. Okay. I think Rashal Verma, he had his question answered. So we don't know what your actual names are. So we just see your Google IDs here. So I don't know if it's Rashal, if I pronounced your first name right, Rashal or Rashal or. Do we have any more questions? So you can ask any question, I mean, related to the assignments. If you find assignments are hard, you can discuss this here now. If you can feel completely free to, or if you find any question was interesting that you would like to share with, it's great. If you found some question was difficult and it lacked, TS can help you out to resolve that part of understanding. So feel completely free to ask questions.
So I have one question. So we have studied some of these concepts of linear spaces and extended it to signal modeling.
Right.
So we have seen that we can construct some basic signals of our own choice to represent signals as points in a linear space. So do we see any practical applications in, using these methods?
Oh yeah, for communication systems. I think you can think about these constellations and all these things, right? QAM, PSK.
So QAM, so these are all like very standard basis signals, sine, omega t, and cos omega t.
Right.
However, are there applications where we design our own basis signals and use them? So which are non-standard or?
We could do that. The Gram-Schmidt essentially does let us do that, right?
Correct.
I mean, if you know the geometry of the signals that you're dealing with, you can design the best basis under the representation. I know I have M signals. Out of M signals, maybe N, which is less than M, form the basis for these signals. And if I know the nature of my signals, using Gram-Schmidt orthogonalization procedure, I can come up with the basis that I want.
So do we see any practical application in or a need to design such basic signals?
Yeah, because it's the best in terms of the approximation, right?
So do we have any practical application? So one I probably have heard is some of these compressive sensing techniques.
Okay, they make use of.
So one is, they can project to an appropriate basis and might represent a signal within a lower dimension. So instead of.
Yeah.
So are there any other, because what I feel is designing some of this basis signal online live when
that's a difficult thing. That's a difficult
thing.
Part. I mean, yeah, the best basis pursuit, etc. Right.
Correct.
So I think, but it gives you the freedom, the flexibility. I mean, either if you know a priori what kind of signals are, then you can do this basis pursuit, whichever you think is ideal. And from there, you can basically represent a signal with the best representation, that is the least in terms of your Euclidean norm, right? You can go about with that. So I think it's just a designer choice, essentially. So
Satyaprakash has another question. He says, he asks if a signal of very small magnitude, say in nanoamperes, and is polluted with higher order noises, how to filter the noise?
I mean, we are talking about the signal to noise ratio here, and if the noise overrides the signal, you are basically negative decibel in terms of SNR, right? 10 log to base 10, the SNR, signal to noise ratio that you get is negative. I think that would, unless there is a very typical signature for your signal that you know that is very narrow on these particular frequencies, then you can basically enhance it and pull the noise out of it. Otherwise, it is not. If you are really a negative SNR, you really are doing it, 0 dB. The information you're conveying is really zero. in such a case. So therefore you cannot. I mean, that depends upon the noise floor. But yeah, but if you know that there is some other properties for the signal, and then you can, you also know the properties of the noise, then you can try and fight out to get the clean signal. I think if you think about most of these Bose acoustic cancelers, right, they do these type of techniques because they actually work with the property of the, yeah. Can you do FFT for long period to get original signal if signal is very weak? No, I just, it's buried, right? What can you do? I mean, if it is, if your signal and noise has the same properties, like for example, I can give you an example of babbled noise, right? You're in a cocktail party, the speech is somebody is talking to you. At the same time, there's a mixture of several other talks by other people that is basically noise, and whose spectrum results like speech, and you add the two together, and if you want to separate out, it's very hard. So there are blind source, these are problems with blind source separation. I read one paper which is for getting gravitational waves. You can please share that paper with us. We don't know
So
exactly.
one way to remove noise is basically make repeated measurements and
Yeah, you
average
just average
them
them. You just average them out. That's just a normal technique. Basically,
Correct.
you're just doing averaging, but that may not be just sufficient.
So a lot of this astronomical data that they collect, it is like they collect over, many samples over time and then average it out.
Right.
To cancel out the noise.
Yeah, averaging is basically like a low pass filtering. So basically, you're removing the out of band noise by averaging. That might be one of the.
It is one is that, and the noise is zero mean. So
yes,
once you average out multiple noise samples,
noise should go out if it is zero mean. But if it is not, then
yes.
So for which you have to collect a lot of ensembles of that
Correct.
data, different time measurements, and then align the phases together, and then you have to basically think about it. Yeah. So we have time till 6:15, right? Because we started.
So we can continue for
another 10 minutes. Okay. Yeah, feel free to ask questions. We have 10 more minutes. Can you throw some light on gravitational wave signal identification? It's something out of my domain, but I can certainly take this question offline, and I can respond back to you via email. Is that fine? So basically, Rohit, can you share your question via email to the TAs? I can dig up a little bit of literature on gravitational waves, and I can explain. If you have very specific questions, I can answer those.
Yeah. So essentially, gravitational wave identification. So what matters from the systems that we are dealing with is only the sensor, right? So the sensor should be specifically tuned to detect the changes in gravitational fields. for the
But I
gravitational.
don't know what this wave is, what your properties are. I have
So
no idea.
the signal processing deals with the properties of those.
Yes, yes.
Okay. Rohit has one more question. Rohit, we have just answered. Sachiprakash has a question. What is the real difference between wavelet transform and empirical wavelet transform?
Well, I mean, wavelet transform is the same thing, right? What is empirical in this? Empirical is something which is done through simulation studies or something. Empirical wavelet transform. I don't know what do you mean by empirical. This is something new to me. Continuous or discrete is what is are the salient. I mean, salient terms in wavelet transformation. I don't know what do you mean by empirical.
So,
Empirical is something decompose a signal or an image on wavelet tight frames which are adaptively built. Yeah, I think that is basically on the fly.
So on the fly, in the sense, we construct the wavelet signals based on the signals that we observe. So it is not any standard.
Not any standard form, but on the fly you build. So I think that might be what empirical means. Okay.
So Shivakumar, how to acquire vibrational data from vehicle drive shaft to predict the crack?
How to acquire vibration data from vehicle drive? So you can place a sensor on your shaft, right? And as it is going through, basically as it is as the wheel is going through, as the rotatory wheel is going through it, it can basically you can record the signature. So basically you can record an as there is a movement, basically there's a torque, and from this rotatory movement you can place a sensor on a portion of the rotating wheel, and as the wheel is going through you can sense a signal that is conveyed through the rotation, and therefore you can acquire that data. And then where there's a discrepancy, where there is a crack, you can basically it shows a dip down or whatever. From that you can basically unfurl the failure analysis.
Maybe the question is also on we'll not be able to keep a sensor on the drive shaft because it is rotating.
You could also have an optical sensor, right? Basically you can just put an optical sensor, just you may not place it on the wheel, but you might have an optical sensor which senses a signal.
Correct.
And then you can place a pointer where because it's an ideal circle, you should have some point where you started off, and then as it is translating, as it is rotating, it is a linear translation.
Correct.
The displacement, right? And you can just basically get that signal through the optical sensor, and then you can basically do the failure analysis to get the crack.
So Nishant has
or digital frequencies, or this is just for 2π. 2π is your sampling, and pi is your Nyquist trade-off.
So what is the significance? So what is the significance of digital frequency? Essentially, we remove the idea of sampling rate in the digital frequency
because there is basically when it is discrete time, it's just a sequence of numbers.
It is a sequence labeled as 1, 2, 3.
That's all. Sequence of numbers. You don't have any unit to the numbers. That's the idea about digital frequency, because we don't have a concept of a meter or a time, temperature, Kelvin or time or whatever. There's just the notion of sequence of numbers. That's all, and that's the idea.
And Nishant has another question on what does negative frequency signify?
I mean, this is a standard thing people ask, right? In 2 negative, basically e power j omega t, e power minus j omega t, add them by 2, that is giving you a cosine signal basically. And basically this is a standing wave. A standing wave can be thought about as 2 different phasors acting in opposite directions, clockwise and anti-clockwise, and you need that to represent the standing wave. And each of the standing wave basically is this, if you think about it in system mode, there are 2 modes in this cosine signal. One is a phasor in this direction, other is other in the other direction, and that basically is giving you a standing wave, and that is basically a resonator, and that you can say is your meaning of a negative frequency. That you
so the other way we can think of is when you have a Cauchy frequency, you can say that the phase is going in clockwise direction. And
yes.
Negative frequency is the anti-clockwise.
Exactly. Just a phasors. That's all. So Rohit said he'll share the paper on gravitational waves. Yeah, please share the paper, and if you have any questions, you can just ask.
So another questions, yeah.
Nishant, I think we answered his question now.
Yes. So yeah, I think we have answered the questions so far.
Yeah, we just have about 3-4 minutes, I guess.
Nish's question.
Nilesh.
Okay.
Where is it? No, we can't see it.
We can't see this here. Can you, if you want, you can read it out.
I want to know, is there any difference between DTFT and DFT?
What is the difference between
discrete DTFT is discrete time Fourier transform, right? The frequency response is continuous, but time is discrete. In DFT, both time and frequency are discrete. That's all.
So Rohit has one more question. If a signal is chosen at random among a discrete set of signals,
Okay,
and then it's observed in additive noise, how can the chosen signal be discriminated?
I mean, you can do maximum likelihood detection on this.
So yeah, we have one problem-solving session on this.
Okay, so you just figure out the likelihood of this signal over the rest of the signals under this noise, and then you can figure out which is what. The one with the least distance metric or maximum in terms of likelihood. I mean, I'm talking about minimization over the Euclidean norm. If it is Gaussian noise, in general, the noise need not be Gaussian, right? Then you can just construct a likelihood function and then do maximum likelihood detection on this to get the right label out. I think one of the problem sets, I don't remember which one of these, but
yes,
I think we
one
just
of the
look into one of the problem solving sessions in the course, and I think the TS have discussed an ML detection idea.
So yeah, it is in week 4 content. So the last lecture of.
Okay, week 4. Rohit, I advise you to look into week 4 lectures and where there are problem solving sessions related to the same question that you have asked.
Yeah, week 3 and week 4 problem solving.
Okay, 3 and 4. Nilesh Bishwas. Sir, I have another question. Yeah.
On the question, what are the practical applications of multi-rate systems?
Oh, plenty. I mean, transmultiplexers, your multimedia coders, right? I mean, the JPEG 4, I mean, MPEG 4 and beyond uses wavelet transformation, which is basically subband coding. Then plenty of applications. And wherever you require a sampling rate conversion, where you don't want to convert it into an analog signal and then again sample back, you use multi-rate signal processing ideas, and also for high decimation filters, because with decimation filters, you can, with lower orders, you can get done with filtering, right? I mean, and than otherwise. Plenty of applications. So I advise you to look into the chapter 4 from Vaidyanathan. Chapters 4 and 5. There's an entire treatment on applications. There, I think section, if I recall, 4.5 and above. Check into those details, and you will have plenty of applications. But I gave you already 3-4 applications. Transmultiplexers, that is TDM to FDM systems. Then we also, for subband coding, for multimedia coders, that is for compression, and then sampling rate conversion without having to convert it back into analog signal and then resample. And all these applications require multi-rate signal processing. So it's now a universal tool. So wherever you are. And also feel free to share your comments on the YouTube videos, and I think it would be very nice for us to get feedback. So I think as you read through the videos, mark your comment and mark your likes as well. It's good for us. And any questions, feel absolutely free to mail the TAs, and they'll pass these questions on to me. Okay, we can wind this up. Yes, yeah. So we'll wind this up, and we'll take this as a feedback. If you think these sessions are useful, we'll have these once in a week now, or once in a week or once in 10 days throughout. I mean, we will decide the frequency depending upon your interest and response, and have these at an appropriate time so that your questions can be answered way well before your final exams. Okay, and as I would like to conclude, I would like to remind you to write your comments on the YouTube videos, your likes, etc., and be proactive in asking questions to the TAs. I can't hear your voice, but certainly I can see your questions, and I can, that's the feedback that I have here. Okay, so good luck, all of you, and have a nice day.